Hello friends, welcome to my second lecture on simplex method. So, here we shall consider some examples where we will have an unbounded solution or we will have more than one optimal solution. Let us consider the case of z equal to 5 x 1 plus 4 x 2, which we have to maximize subject to the conditions x 1 less than or equal to 7, x 1 minus x 2 less than or equal to 8, x 1 x 2 are non-negative. We shall see that in the case of this LPP we have got an unbounded solution. So, we will convert it into the standard form. Maximum of z equal to 5 x 1 plus 4 x 2 plus 0 s 1 plus 0 s 2. S 1 s 2 are two slack variables which are being used to convert the constants into equations. So, x 1 plus s 1 equal to 7, x 1 minus x 2 plus s 2 equal to 8. Okay. X 1 x 2 s 1 s 2 are all non-negative, s 1 s 2 are two slack variables. Now, let us write the corresponding first simplex table. So, we will have the simplex table as C j row contains the coefficients of the variables in the objective function. So, 5 4 0 0, okay, 5 4 0 0 they are the coefficients of x 1 x 2 s 1 s 2. The basis elements are s 1 s 2, basic variables are s 1 s 2, their coefficients in the objective function are 0 0, and the body matrix is 1 0, because the coefficient of x 1 is 1, coefficient of x 2 is 0. So, 1 0 and then 0 minus 1, the coefficient of x 1 is 1 here, coefficient of x 2 is minus 1. So, body matrix is 1 0 0 minus 1, and the other matrix is the unit matrix. So, 1 0 okay, 0 1. Under B column we have the constants which occur on the right side of the equations. They are 7 and 8. So, we get 7 and 8 here. Now, let us find the zj value. Zj equal to sigma Cb Aij. So, z1 for the column j equal to 1. Okay, we have 0 into 1 plus 0 into 1, that is 0. So, we get 0 here, and then Cj, capital Cj is 5 Cj small cj minus zj. So, 5 minus 0 is 5. Okay. Then similarly, z in 0 into 0 is 0, 0 into minus 1 is 0. So, we get zj for j equal to 2 equal to 0, and then Cj is equal to 4 minus 0. So, we get 4 here, and then 0 into S1, 0 into 1 is 0, 0 into 0 is 0. So, we get 0 here, 0 minus 0 is 0, and then we get 0 into 0, 0 into 1. So, 0. So, we get 0 here, 0 minus 0 is 0 here. Now, we can see Cj is positive for j equal to 1 and 2. Okay. Cj is greater than 0 when j is equal to 1 and 2, and the maximum value of Cj is 5. Okay. So, this is our key column. Okay. Now, let us find key row. So, we divide the elements of V column by the corresponding elements in the key column. So, 1 divides 7, we get 7 by 1 equal to 1 and 8 by 1 equal to 8. Now, we consider the minimum positive ratio. So, this is 7, this is 8, minimum positive ratio is 7. Okay. So, this is our key row. Okay. So, at the intersection of key row and key column we have 1 here, this is key element. Okay. Since it is already 1, we do not have to make it into 1, it is. So, what we will do, we will then make this element 0 in the other row. Okay. In the key column we make, with the help of the key element, after it has been converted into unity, all the other elements in the key column 0. So, there is on this 1 we have to make it 0. So, we subtract this row, okay, key row from the second row, and then what we will get? We will get 1 0, this key row is 1 0 1 0 7. Okay. And here it will become, after subtracting this second row will become 0, and then we will get minus 1, then we get 0 minus 1. So, we get minus 1, 1 minus 0 is 1. Okay. And here we get 8 minus 7 equal to 1. Okay. And this variable, okay, S1 will be outgoing variable, x 1 will be incoming variable. So, in the new simplex table we will have C b, okay, basis. So, basis will contain variables x1, s2, the coefficient of x1 is 5, coefficient of s2 is 0. Okay. We have x1, x2 and then s1, s2 and b. Okay. The key row is 1, 0, 1, 0, 7. Okay. And we have subtracted key row from the next row, okay, which became 0, minus 1, then we had minus 1, then we had 1, then we had 8 minus 7 1. Okay. So, this is our new table. Let us see the new table. We have CV column contains 5 0, x 1 s 2, 1 0 1 0 7, 0 minus 1 1 1. Okay. Now, let us find z j value. So, 0 5 into 1 is 5, 0 into 0 0. So, we get 5 here, 5 minus 5 is 0, and then 5 into 0 is 0, 0 into minus 1 is 0. So, we get 0 here, 4 minus 0 is 4, and then 5 into 1 is 5, this is 0. So, we get 5 here, 0 minus 5 is minus 5, then 5 into 0 is 0, 0 into 1 is 0. So, we get 0 here, 0 minus 0 is 0. Now, we can see 5 into 7 is 35, this is 0. So, this is 35 CB into B column. Okay. Now, we have to see Cj is positive in the column j equal to 2. Okay. So, this is our key column. Okay. This is our key column, and so the elements of the key column are 0, minus 1. We will divide the corresponding elements in the B column. Okay. So, 7 divided by 0, we get here 7 divided by 0, then 1 divided by minus 1, we get this. Now, we have to consider only positive values in the theta column to determine the minimum positive theta. Okay. So, minimum positive value is only 1, that is 7 by 0. Okay. So, minimum positive value is infinity, and therefore, it is not possible to proceed with the simplex computation any further, and so we get an unbounded solution here. Okay. Now, let us consider second problem. We have the function objective function z equal to 2000 x 1 plus 3000 x 2, and we are given two constants 6 x 1 plus 9 x 2 less than or equal to 100, 2 x 1 plus x 2 less than or equal to 20. X 1 x 2 are two non-negative variables. Okay. We introduce select variables x 1 x 2 to convert these constants into equations. So, 6 x 1 plus 9 x 2 plus s 1 equal to 100, 2 x 1 plus x 2 plus s 2 equal to 20, and in the objective function we take the coefficients of s 1 s 2 as zeros. Okay. So, z maximize z equal to 2000 x 1 plus 3000 x 2 plus 0 s 1 plus 0 s 2, x 1 x 2 s 1 s 2 are greater than or equal to 0. Now, let us write the first simplex table. So, Cj column contains Cj row contains 2000, 3000, 0, 0, which are the coefficients of x 1 x 2 s 1 s 2. Basis variables are s 1 s 2, their coefficients in the objective function are 0, 0. Okay. Body matrix is 6 9 2 1, that is body matrix 6 9 2 1, and the unit matrix is 1 0 0 1. Okay. Now, we have to find the zj value. Theta column is the B column is containing 120, these are the values 120 which constitute the V column. Okay. Now, let us find zj, z1 j equal to 1 we take. So, 0 into 6, 0 into 2. So, we get 0, 2000 minus 0 is 2000. Okay. Similarly, 0 into 9 is 0, 0 into 1 is 0. So, we get 0 here as z2 value is z2 value j equal to 2, j equal to 2 gives z2 is 0, 3000 minus 0 is 3000. Then 0 into 1 is 0, 0 into 0 is 0. So, we get 0 here, 0 minus 0 is 0, and then 0 into 1 0 is 0, 0 into 1 is 0, we get 0 here, 0 minus 0 is 0. Now, so Cj is greater than 0 for j equal to 1 and 2, the maximum value is 3000. So, this is our key column. Okay. The elements of V column are divided by the corresponding elements in the key column. So, 100 over 9 we get, and 20 by 1 we get. Okay. We take the minimum positive ratio. So, 100 by 9 is minimum ratio here. So, therefore, this is our key row. Okay. At the intersection of key row and key column we have 9. So, key element is 9. Okay. We divide, okay. So, this means what? This means that S1 is outgoing variable, okay. S1 is outgoing variable, X2 is incoming variable, and therefore, the new simplex table will be CB in place of 0. Now, we will have S1 is outgoing, X2 is coming in. So, X2 coefficient of X2 is 3000. So, 3000, okay, basis will contain X2 and S2, okay, and here will S2 as coefficient of S2 is 0 in the objective function. We have X1, X2, S1, S2, B. So, this is 2000, this is 3000, this is 0, this is 0, this is Cj, okay, small Cj, and then we divide the key row by the key element. So, we divide the key row by 9 because 9 is the key element, and we get here 6 by 9. 6 by 9 means 2 by 3. Okay, so, this is 2 by 3, this is 1 here, this is 1 by 9, this is 0. Okay. We are dividing by 9, and then we get 100 by 9. Okay. Now, once we have made this key element 1, we subtract suitable multiples of it from the other rows, okay, to make the other elements in the key column as zeros. So, this is 1, okay, and this is also 1. So, we subtract we subtract this row from the second row. So, we get 2 minus 2 by 3, and we get 1 minus 1 0, and then we have here 0 minus 1 by 9. So, minus 1 by 9, and here we get 1 minus 0. So, we get 1 here, and then 20 minus 100 by 9. So, how much is this? 4 by 3. Okay. So, what we get in the next table, let us see. So, 3000 0 x2 s2, okay, x2 s2, and 2 by 3 4 by 3, that is first column, 2 by 3 4 by 3. The second column is 1 0, okay, 1 0. Third column is 1 by 9 minus 1 by 9, 1 by 9 minus 1 by 9, 1 0, and then 0 1, okay. So, we have 0 1, okay, 0 1. Then B column becomes 100 by 9 and 80 by 9, okay. So, 80 by 9, okay. So, here you can see 100 by 9 and 80 by 9, 80 by 9, okay. Now, let us find Cj Zj value. Zj is equal to 3000 into 2 by 3, that is 2000, this is 0. So, we get 2000 here, 2000 minus 2000 is 0, and here we get 3000 into 1. So, 3000, 0 into 0 0, so we get 3000, 3000 minus 3000 is 0, then we get 3000 into 1 by 9. So, we get 3000 into 1 by 9, that is 1000 by 3, and this is 0. So, we get 1000 by 3, 0 minus 1000 by 3 is minus 1000 by 3, okay. So, this is minus 1000 by 3, and then we get 0 into 3000, 0, 0 into 1 0. So, we get 0 here, 0 minus 0 is 0. So, we get 0 here. Now, so we see Cj is 0, 0 minus 3 by 1000 by 9, 0, okay. So, Cj is less than or equal to 0 for all variables, okay. Basic variables are x2 and s2, okay. So, x2 is equal to 100 by 9, s2 equal to 80 by 9, x1 is equal to 0. So, x1 is equal to 0, x2 equal to 100 by 9 is an optimal solution of the LPP. The maximum value of the objective function is, you can see z equal to we had 2000 into x1 plus 3000 into x2 plus 0 s1, 0 s2, x1 is 0, x2 is 100 by 9, okay. So, 0, x1 is 0, so 3000 into 100 by 9. So, what we get is 100,000 divided by 3, okay. So, 100,000 by 3. However, Cj value corresponding to the non-basic variable. Now, x1 is a non-basic variable, okay, and Cj value corresponding to the non-basic variable is 0. Okay. Cj value corresponding to non-basic variable x1 is 0. This indicates that there is more than one optimal solution of the problem. So, what do we do? By entering x1 into the basis, and we may obtain another optimal solution. Okay. So, if you take this as key column, okay, and this minimum positive ratio here you see 1000 by 9. Okay. We have this we take as key column. If we take key column, then we have to find key row. So, we divide by 4 by 3. So, 80 by 9 into 3 by 4. So, we get 20 by 3. Okay. And then 2 by 3, when 100 by 9 is divided by 2 by 3, we get 3 by 2. So, 50 by 3. Okay. So, we get 50 by 3. Okay. Now, we have to take minimum value. So, 50 by 3 is more than 20 by 3. So, this is key row. Okay. This key row at the intersection of key row and key column, we get 4 by 3. So, this is key element. Okay. So, we divide key by 4 by 3. Okay. Now, what will happen? X2 will be incoming variable, S2 will be outgoing variable. Okay. And we will have the following table. So, 3000, 2000, x2, x1. Okay. And we divide this by 4 by 3. So, this will become 1 0 and minus 1 by 9, minus 1 by 9 into 3 by 4. So, minus 1 by 12, we are dividing by 4 by 3. So, minus 1 by 12 we have, and then 1 divided by 4 by 3. So, 3 by 4 we have. So, this is 3 by 4. Okay. And then 80 by 9 divided by 4 by 3. So, that makes it 20 by 3. So, this is 20 by 3 here. Okay. Now, this element which has become 1. Okay. This element which has become 1, with the help of this we make the other entry in the x1 column 0. Okay. So, this has become 1, this we have to make 0. So, we multiplied by 2 by 3 and subtract from this row. So, this will become 0. Okay. We are multiplying the new row, new key row by 2 by 3 and subtracting from this row. Okay. So, we have so what we have 2 by 3 we multiply here, so and subtract here. So, this becomes 0. This is already 0. So, it will not be changed. This is 1, and minus 1 by 12, minus 1 by 12 we are multiplying by 2 by 3. Okay. So, 2 by 3. So, minus 1 by 18, we are multiplying by 2 by 3 and subtracting from the first row. Okay. So, what is that? 1 by 9, 1 by 9, 1 by 9 plus 1 by 18. This gives us 1 by 6. Okay. Similarly, this becomes minus half and this becomes 20 by 3. How that is 20 by 3? We have 100 by 9, 100 by 9 we have. Okay. And this is 20 by 3. So, minus 20 by 3 into 2 by 3. So, this is 40 by 9 we get. So, 60 by 9 we have, okay, which is 20 by 3. So, this is 20 by 3. Okay. Now, we find Zj. Zj is 0 into 3000, 0 1 into 2000. So, 2000 here, here it is 3000, here it is 1000 by 3. 2000 minus 2000 is 0, 3000 minus 3000 is 0, 0 minus 0 0, this is minus 1000 by 3. Now, you can see value of the objective function will be how much. So, x2 3000 x2 we have. Okay. So, 3000 into 20 by 3. Okay. Z will be equal to 3000 into 20 by 3 plus 2000 into 20 by 3. So, this is 20 into 3000. So, 60,000 plus 40,000. So, we get 100,000. So, we get the same objective value of the same value of the objective function. Okay. but the present solution is now x 1 equal to 20 by 3, okay, x 1 equal to 20 by 3 and x 2 equal to 20 by 3. Okay. So, the solution is of course has changed from x 1 equal to 0, x 2 equal to 100 by 9 to x 2 equal to 20 by 3, but the value of the objective function remains the same. So, we have multiple optimal solutions, but the objective function's value is the same. Okay. So, now let us go to degeneracy. Degeneracy is in a linear programming problem is said to occur when a basic feasible solution contains a smaller number of non-zero variables, okay, than the number of independent constants when values of some basic variables are 0. Okay. So, and the replacement ratio theta is the same. In other words, under simplex method, degeneracy occurs when there is a tie for the minimum positive replacement ratio theta. So, when the theta is same for when there are two values which are same in the theta column, okay, then it is then we can then how to make choose the outgoing variable. In this case, the choice for selecting outgoing variable can be made arbitrarily. So, when in the theta column we have two values which are same, then how to determine the minimum positive replacement ratio. So, we can select any one as the minimum positive replacement ratio if there is a tie. So, the choice for selecting outgoing variable may be made arbitrarily. Let us take an example on this. Suppose we have maximum of z equal to 3 x 1 plus 9 x 2, x 1 plus 4 x 2 less than or equal to 8, x 1 plus 2 x 2 less than or equal to 4. Take two select variables s 1 s 2 and bring the LPP into standard form. So, 3 x 1 plus n 9 x 2 0 s 1 0 s 2, x 1 plus 4 x 2 plus s 1 equal to 8, x 1 plus 2 x 2 plus s 2 equal to 4, x 1 x 2 s 1 s 2 greater than or equal to 0. Now, we can write the simplex table. So, coefficients of x 1 x 2 are 3 9, coefficient of s 1 s 2 are 0 0, basis variables are s 1 s 2, their coefficients in the objective function are 0 0, a body matrix is 1 4 1 2. Okay. Let us see 1 4 1 2, okay, and the unit matrix is 1 0 0 1. Okay. This is 1 0 0 1. Then we can find zj. Zj we can find 0 into 1 0 into 1. So, 0 3 minus 0 is 3 and then 0 into 4 is 0, 0 into 2 is 0, 3 minus 9 minus 0 is 9, 0 into 1 is 0, 0 into 0 is 0. So, we get 0 minus 0 equal to 0, then 0 into 0 is 0, 0 into 1 is 0, we get 0, 0 minus 0 is 0. Now, there are two values of Cj which are positive. When j is 1, we get C1 equal to 3 and C2 is equal to 9. Okay. So, we get take the maximum of these two. So, and 9 is obviously the maximum. So, key column is this one, this is key column. Okay. Now, the elements in the key column are 4 and 2. Divide the B column values by these key column values. So, 8 by 4, okay, and then 4 by 2. Now, you can see this is 2, this is 2. Both the values of theta are positive and they are equal, they are equal. So, how to find the minimum positive theta? Minimum positive theta is 2. Okay. So, there is a tie and therefore, it is how to select the outgoing variable. So, we can choose any row as the key row. Okay. Let us choose this row as the key row. Okay. Then at the intersection of key row and key column we have 2. So, this 2 is key element. Okay. So, we divide this row by 2. Okay. So, then now what will happen? S 2 will be going out, okay, and x 2 will be coming in. So, new simplex table will be CB 0 basis we have S 1 and here we will get in place of x 2 x 2, the coefficient of x 2 is 9. Okay. And we will have here this row will now be divided by 2. Okay. So, we will have 1 by 2 1 0 1 by 2, okay, 4 is divided by 2. So, we get 2 and we have x 1 here, x 2 here, s 1 here, s 2 here, b here. Okay. Now, this new row, okay, in the new row this key element has become 1, we multiply suitably this row and subtract from the other row to make it the corresponding element in the key column 0. So, here it is 4. So, we multiplied by 4 and subtract from here. So, 4 into half is 2, 1 minus 2 is minus 1, then 4 minus 4 is 0, then we get 1 minus 0 is 0, oh sorry 1 minus 0 is 1. So, we get 1 here, and then here we have 0 and here we have half. Okay. So, we multiply by 4. So, 4 into half is 2, we are subtracting 2 from 0. So, we get minus 2 here, and here we are multiplying by 4. Okay. So, 8 we are subtracting from 8. So, we get 0. Okay. Now, so this is our new table. Let us see. So, let us go to the next table, CB 0 9. Okay. We have 0 9, then S1 X2, S1 X2 we have minus 1 0 1 minus 2, minus 1 0 1 minus 2, okay, minus 1 0 1 minus 2 0 we have. So, let us see, yeah, this is okay. Then half 1 0 half, half 1 0 half 2, half 1 0 half 2. Okay. Now, we find ZJ here. So, 0 into minus 1 G 9 9 into half. Okay. So, we get 9 by 2. Okay. 0 into minus 1 is 0, G 9 into half is 9 by 2. So, it should be 9 by 2. So, 3 minus 9 by 2 will give us capital Cj. So, this is 6 minus 9 by 2 will become minus 3 by 2. Okay. And then here what will happen, 0 into 0, 0 and 9 into 1. So, 9. So, this should be 9. Okay. So, 9 minus 9 is 0, then 0 into 1 is 0, 9 into 0 is 0. So, we get 0 here, 0 into minus 2, 9 into half. So, we get 9 by 2. So, this is 0 minus 9 by 2 is minus 9 by 2. Okay. Yeah, and then 0 into 0 0, 9 into 2 18. So, this should be 18. Okay. This should be 18. Now, what this Cj values are minus 3 by 2 0 0 minus 9 by 2. So, Cj is less than or equal to 0 for all j. Okay. So, optimal solution is x1 equal to 0, x2 equal to 2, okay, x2 equal to 2 and z equal to 18. Okay. So, here what we have got, maximum value of z is 18, x1 is 0, x2 is 2. Now, this we got while we considered this row as the key row. Let us see, if I select this row as the key row, then what happens. So, if we do that, what will happen? Yes. So, if I take this as the key row, okay, suppose I take this as the key row, then what will happen, x1 will be going out and x2 will be coming in. Okay. So, the new row will be CB, we will have this element will be our key element now. Instead of 2, we will have 4 now as key element. So, x2 will be coming in place of s1. The coefficient of x2 is 9. So, we have 9 0 basis will be having x2 here, x2 will be coming in place of s1 and we have s2 here. Okay. Yes, and we will have here 3 9 0 0 x1 x2 s1 s2. Okay. After we have replaced this s1 by x2, we divide this row by 4. Okay. So, we get 1 by 4, we get 1 here, we get here 1 by 4 and we get here 0 and we get here 2. Okay. Now, with the help of this element 1, okay, this element 1, we make this element 0. So, we multiply it by 2 and subtract from here. So, this 2 by 4 we subtract from 1. So, we get 1 minus half. So, we get half here, then this is 2 minus 2 is 0, then this is 0 and here it is 1 by 4, so we multiply 2. So, we get minus half here and we multiply it by, we are multiplying by 2, right, and subtracting from this. Okay, so this will remain 1. Okay, and we are multiplying by 2, so this will come 4. 4 we subtract from 4, we get 0 here. Okay, so let us see what we have there. You see, we have x2 s2. Okay, and we have 9 0 here. These elements are 1 by 4 1, 1 by 4 0 2, 1 by 4 1, 1 by 4 0 2, and we have half 0 minus half, half 0 minus half, and we have 1 0. Okay, right. So now we go there and we find the zj. Zj is 0, 9 into 1 by 4, 9 by 4, 0 into half, so this is 9 by 4, 3 minus 9 by 4, 3 minus 9 by 4 gives you 3 by 4. So we get 3 by 4 here, and then 9 into 1 is 9, 0 into 0 is 0. So we get 9 here, 9 minus 9 is 0, and then 9 by 4, 9 into 1 by 4 is 9 by 4, this is 0, so 9 by 4, 0 minus 9 by 4 is minus 9 by 4, 9 into 0 is 0, 0 into 1 is 0, so we get 0, 0 minus 0 is 0. Okay. So Cj is positive for j equal to 1, C1 is greater than 0. So this is key column. Okay. Let us find the theta value. So 1 by 4 we divide 2 is divided by 1 by 4, we will get it 8. Okay, and here what we get 0 divided by half, so we get 0. Okay, so minimum of the value is this 0. Okay, so this is kilo. Okay, we divide kilo by half. Okay, so what we will get, this will become 1, this S2 will be replaced by what, S by yeah, x1. Okay, so basis will be our x2 x1. Okay, CB will be 9 and 3. Okay, x, now what, so this row will become, after dividing by half, it will become 1 0 minus 1 2. Okay, and we are dividing by half, so this will remain 0. Okay, now with the help of this 1 we make this 0. Okay, so we multiplied by 1 by 4, subtract from there, so 0, 1 by 4 we multiply to this and subtract from there, so we get 1, 1 by 4 we multiply here, so minus 1 by 4 we subtract from there, so we get 1 by 2, and then 1 by 4 we multiply here, 2 by 4 means half, half we subtract from 0, so we get minus half, and we multiply it by 1 by 4 and subtract from there, so this will remain 2. Okay, yes. So let us see the new table. So we get 9 x1, this should be 3. Okay, we get 0 1 half minus half, 0 1 half minus half 2, 0 1 half minus half 2, 1 0 minus 1 2, 1 0 minus 1 2 0. Okay, yes. Now let us say find zj. So 9 into 0 0, 3 into 1 is 3, 9 into 0 is 0, 9, 3 into 1 is 3, so this should be 3. Okay, 3 minus 3 is 0, then 9 into 1 is 9, this is 0, so we get 9 and 9 minus 9 is 0, then we get 9 into 1 by 2, 9 by 2, and this is minus 3, 9 by 2 minus 3, so we get 3 by 2. This is 3 by 2, and then 9 into minus half, minus 9 by 2, 3 into 2 6, so minus 9 by 2 plus 6, so minus 3 by 2. Oh sorry, this is 12 minus 9, 3 plus 3 by 2, so 3 by 2 we will have here. Okay, so 9 minus 9 by 2 plus 6, so 3 by 2 here. So 0 minus 3 by 2 is minus 3 by 2. Okay, now Cj is less than or equal to 0 for all j. So what we have, x1 equal to 0, okay, x1 equal to 0, x2 equal to 2. So x1 equal to 0, x2 equal to 2, and 9 into 2 is 18, and 3 into 0 is 0, so z is equal to 18. So we get the same value of z. Okay. In the previous case we had x 1 equal to 0, x 2 equal to 2, z equal to 18, and optimal solution was x 1 equal to 0, x 2 equal to 2, z equal to 18, and by making the other choice again we get the same optimal solution. So, we can choose when there is a tie in the theta column, when there is a tie for the minimum positive replacement ratio for selecting outgoing variable, okay, the choice for selecting outgoing variable can be made arbitrarily. This we can see from here, okay. We get the same solution. Okay. So, we have discussed various cases, the cases where we found an unbounded solution, the case where we found more than one optimal solution, and also the case of degeneracy where we discussed a problem where the value of in the theta column were same. So, to how we were not able to decide which one to take as the minimum positive ratio because of a tie. So, the selection of outgoing variable how it should be made we had discussed, and we saw that that choice can be made arbitrarily. In both the cases we get the same optimal solution. So, in case of a tie in the theta column, the choice for selecting outgoing variable may be made arbitrarily. So, with that I would like to end my lecture. Thank you very much for your attention.